Most centrifugal pumps are operated singly. That is, one pump discharges into a pipeline. But in some circumstances, series operation is desirable. Two pumps operate in series when the first pump discharges into the suction of the second. To learn the effects of series operation, let's look at the first of the two pumps. And note the suction, discharge, and total heads, and the pumping rate. For example, let's say suction head is 0 and discharge head is 100 feet. Then the total head is 100 feet. Let's say pumping rate is 100 gallons of water per minute. Now look at the second pump. For simplicity, let's assume it's exactly like the first. If so, like the first pump, it can develop 100 feet total head. But this pump has a suction head of 100 feet, the first pump's discharge. So the second pump has a discharge head of 200 feet. Now, the second pump can't pump any more liquid than it receives from the first pump. But it pumps at a greater head, a higher discharge pressure. Operating pumps in series can be useful when the head required is greater than either pump can develop alone. But an increase in volume is not required. Because both pumps in series must pump at the same rate, they should have about the same capacity ratings. Otherwise, one or both pumps may be damaged. The second pump casing must be able to withstand the higher discharge pressure. Pumps have been ruptured when this requirement was overlooked. And of course, the pipeline system the pumps discharge into must be strong enough to stand the higher discharge pressure. We have discussed only two pumps in series. It's possible to use more, but for more than two, the discharge pressure of the last pump might be excessively high. Cross-country pipelines may have many pumps in series, but friction in the long lengths of line prevents excessive pressure buildup. Pumps that discharge into the same pipeline system like this are said to be operating in parallel. One of these pumps, working alone, has its own individual capacity at a given total head. Let's say one pump, working alone, develops a total head of 135 feet and a capacity of 275 GPM. If each of the two pumps develops about the same head, their combined capacity when operating in parallel is greater than the capacity of either pump working alone, but not as great as the sum of the individual capacities of the pumps when each is working alone. Pump capacity, flow rate, cannot increase without an increase in the discharge system pressure differential, abbreviated delta P. In fact, delta P varies as the square of the flow rate. To increase delta P, pumps in parallel cannot decrease the pressure at the end of the discharge system. They increase their discharge pressure. They increase their total head. Suppose the total head increases to 150 feet. Then either pump, working alone at this head, if they are identical, has a capacity of only 200 GPM. Pumping in parallel, their combined capacity is 400 GPM. For effective parallel pumping, it's not necessary that the pumps have similar capacities. If they do not, be sure to use each pump's own characteristic curve in estimating capacity at the total head developed. It is necessary for effective parallel pumping that pumps have about the same head characteristics. If one pump develops a high discharge pressure and the other a low discharge pressure, the second pump cannot discharge into the system. When head characteristics are similar, capacities, as reduced by increased total head, are additive. Summarizing, to increase head, operate pumps in series. To increase capacity, operate pumps in parallel. Now turn to workbook number 2 and complete exercise 14. To demonstrate your knowledge of pump operations, you will be required to calculate such things as liquid horsepower, brake horsepower, and pump efficiency. If you are given the conditions under which a pump is operating, you can calculate the liquid horsepower put out by the pump. For example, a centrifugal pump is pumping water at a rate of 100 gallons per minute and with a total head of 200 feet. What is the liquid horsepower? A logical approach to solving this problem is to calculate the pump's power output in foot-pounds per minute, since we know how to convert foot-pounds per minute to horsepower. The pumping rate is given in gallons per minute. Converting this quantity of water to pounds per minute provides the necessary ingredients to calculate foot-pounds per minute. To convert to pounds per minute, multiply the number of gallons of water by its density, 8.33 pounds per gallon. The result is 833 pounds per minute. Next, calculate the power produced in foot-pounds per minute. The pump is lifting 833 pounds of water, the equivalent of 200 feet every minute. 833 pounds per minute times 200 feet equals 166,600 foot-pounds per minute. The final step is to divide the foot-pounds of work being done per minute by the number of foot-pounds per minute per horsepower. The liquid horsepower for the pump is 5.05. The power input, brake horsepower, must be greater than 5.05 to produce 5.05 liquid horsepower. How much greater depends upon the pump efficiency. Rearranging the formula and solving for brake horsepower equals 5.05 horsepower divided by efficiency. If the pump efficiency is 70%, we substitute 0.70 in the formula and then calculate the brake horsepower to be 7.2. Therefore, we see that the motor must produce 7.2 brake horsepower to produce 5.05 liquid horsepower in a pump with 70% efficiency. Now turn to workbook number 2 and complete exercise 15.